the pH of an acid as base is added. Let's say maybe we have NaOH, and we're titrating a acid, in this case hydrochloric acid. So the pH starts out very low if it was HCl, and changes gradually up to a point where it changes to be more basic. So if this would be neutral, 7, here's 14, 0. This would be the way pH changes for HCl. As base is added, the pH rapidly changes and goes from being very basic to very acidic to being very basic. So this is not good for a lot of reactions, especially reactions that happen in the body, in biochemistry. So reactions inside living systems are very sensitive to pH. In fact, in the body, in our blood, pH has to be maintained at about 7.35 to 7.45, right at a narrow. So in order to maintain that range, a buffer is used in biochemistry as well as many other applications. Buffers are weak acids or bases. So we saw the action of a weak acid or base. It might start about here, and we have this gradual line before it eventually will go up. So weak acids and bases provide a large area of stabilization. So it buffers the pH where the pH doesn't change very much, as opposed to strong acids and strong bases. So we can use different buffers depending on what we need, or the pH that we need. Some might have a pH range like the carbonic acid that's, let me use a different color, that's up here. And so we can use a different range depending on what pH needs to be maintained. Now, buffers consist of a weak acid with their conjugate base. So, for example, the carbonic acid and bicarbonate buffer system, the one that maintains is H2CO3, so that's carbonic acid, in combination with its conjugate base, CO3 bicarbonate. So here we have acid, conjugate base. In order to have concentrations of both of these to get the capacity, some additional conjugate base would be added in this case, and it gets added in the form of sodium bicarbonate. So that gets added to increase the concentration so that we have an adequate amount of both acid and conjugate base. Why do we add it in the form of a salt? Something that neutralizes the negative charge here. Well, just for that reason. We can't have negative charges just floating around by themselves. So there has to be something to neutralize it. That's why we have the sodium in conjunction with the bicarbonate ion. During dissociation, the ion is what really has the effect and functions as the conjugate base. So for this first example, the Ka given to us, so the acid dissociation constant, and we have a buffer prepared with acetic acid and acetate ion. And we want to know the pH of this buffer. So the first thing we can do is we can write out the equation for that, and it happens to be given to us here actually. So this is our equation for that reaction. The acetic acid reacts with water to make hydronium and acetate ion. So we can see that the proton is being donated from the acetic acid to water, giving us hydronium, and then the leftover here acetate from the acetic acid. Now, in this reaction, the acid is the acetic acid, and its conjugate base is the acetate ion. So it's these two, the acid and its conjugate base. These two are what will provide the buffering capacity, this weak acid with its weak conjugate base. So we are given concentrations of each of those, and we can use the acid dissociation expression to figure out the pH. Let's see how this works. Well, the first thing we would do is write down our information. Ka is 1.8 times 10 to the negative fifth. And then we have the concentrations. That's the acetic acid concentration is 1.0 molar. And the acetate ion is also 1.0 molar. We want to know pH. Well, we're going to use this equation to write out the acid dissociation expression. So if we write out the expression from this equation, Ka is the products multiplied together, right? We've seen this before. Let's back up here and we'll review for a second. So here we have the dissociation expression. We have the products divided by the reactants concentrations, and we leave out water because it's a pure liquid. So we're going to right now for this reaction. So we have the products, hydronium and acetate ion, times CH3COO minus, all divided by the acetic acid, CH3COOH. Now, we want to know pH, and the key here is to recognize that pH is the negative log of the hydronium ion concentration. So we need to find hydronium. Once we have hydronium, we can just do one more step and we'll know the pH. Well, we have all the other numbers here. We can solve for hydronium and then just take it one more step. So we do the algebra. We would need to multiply both sides by this term, divide both sides by this term to isolate H3O plus. And so it comes out to Ka times CH3COOH, all divided by CH3COO minus. And so we can substitute those numbers. Ka is 1.8 times 10 to the negative fifth, multiplied by 1.0 molar, divided by 1.0. So H3O plus is simply 1.8 times 10 to the negative fifth. So now we just have one more step. The pH is the negative log of the hydronium ion concentration. The pH then is the negative log, base 10, of 1.8 times 10 to the negative fifth. So we have 1.8 E5 negative times 10 to the negative fifth log negative. And so that's 4.74. Let's do another example. So in this problem, it says one of the conjugate acid-base pairs that buffers in the blood is the phosphoric acid and HPO 4,2- ion system with a Ka shown there. We want to know the pH given it's 0.1 molar H2PO4 and 0.5 molar HPO4 2-. So let's write out the reaction for this. We have H2PO4 minus, and this reacts with water, and since H2PO4 is functioning as an acid, it donates to water, and we'll get HPO4 2- and also H3O+. Now, the expression given this, Ka, is, so we have the acid here and its conjugate base here. These two are having the buffering capacity. To write the acid dissociation expression, we're going to have the concentration of these two multiplied together, HPO4 times H3O+, all divided by H2PO4-. And we're given concentrations in the problem. We're given also Ka. Ka is 6.2 times 10 to the negative 8th. The HPO4 2- is 0.50 molar. And the H2PO4 minus, that is 0.10 molar. Again, we want to know pH. So here's our list of givens and unknowns. So we approach this in the same way as before. If we can solve for H3O+, we can do one more step, and then we'll know the pH. So H3O+ is Ka times H2PO4 minus concentration divided by HPO4 2- concentration. And so H3O+ is Ka 6.2 times 10 to the negative 8th times H2PO4 minus, so that's 0.10 molar, 0.10 divided by H2PO4 2- 0.50, and so we calculate that. Times 0.1 divided by 0.5. And so 1.24 times 10 to the negative 8th. And now we have just one more step. The pH is the negative log of the hydronium ion concentration which is 1.24 times 10 to the negative 8th. So the pH is the negative log of the hydronium. The concentration, we're using that to find pH. Last step is just calculate this. So 1.24 times 10 to the negative 8. Log of that, negative. So the negative log then is 7.9. 7. I'm rounding to 3 decimal places here because there were 3 places in the coefficient which match the places after the decimal. Now there is another way to solve these problems as well. There's a formula, and the formula pH equals pKa plus the log base 10 of the conjugate base divided by the acid concentration. Let's see how it would look if we plugged it into the formula. And this is called the Henderson-Hasselbalch Equation. So if we plug this in, the pK is the pH, except it's for the Ka. So if we take the pKa of that, 6.2 E8 negative. So we have this number. I'm going to take the negative log of that, just as if I was doing the pH. So the pH then is 7.2 1 plus the log base 10 of the acid divided by the conjugate base divided by the conjugate acid. So conjugate base concentration was the HPO4 2 minus, so that would be 0.5 divided by the acid, which was 0.1, so that's 5. And we take the log base 10 of that, it's 0.669 698 699. Alright, so if we add those two together, we'll end up with the same number, 7.907. And there we go. So that's another way to solve it. It involves using a formula. And so you'd have to memorize the formula. This other way is just using the concepts that we've learned already. And so there's no new formula to memorize, just solving the procedure of solving for H3O plus and then using the pH equation to find the pH.